Yeah, okay.
Is it 5:30 yet? Is this working? Yeah. Is it 5:30? Another minute?
Yeah.
Better like this? Okay. Well, good evening, everybody, and welcome to our lecture tonight. And before we begin tonight's program, I want to express our deep gratitude to Lucky Vidmar and his wife, Aubrey, whose generosity has made this lecture series, the Moulakis lecture series on responsible engineering, even possible. This lecture, thank you. Thank you so much. So this lecture honors one of our program founders, Thanasis Moulakis, the Herbst Program for Engineering, Ethics and Society, and reflects a shared commitment to fostering education, dialogue, and engagement. Thanks to Lucky and Aubrey Vidmar's support, we are able to bring distinguished voices to our community and create opportunities for reflection and exchange that enrich us all. We are honored by their partnership and sincerely thank them for making tonight's lecture in this entire series even possible. It's a great honor tonight to introduce you to our very distinguished speaker tonight, Dr. Moriba. Currently, Dr. Jha is a professor of aerospace engineering and engineering mechanics at the University of Texas at Austin, where he is the holder of the Mrs. Pearlie Dashiell Henderson Centennial Fellowship in Engineering. Dr. Jha is many things at once, and it was really hard to write this introduction, actually. He's a world-class scientist, a pioneering engineer, an entrepreneur, a MacArthur Fellow, and a National Geographic Explorer, and so many more things. Dr. Jha's life is truly global in his education. Research and life are just remarkable. After serving in the Air Force, he pursued aerospace engineering and at Embry-Riddle Aeronautical University, inspired by the possibilities of astrodynamics. He went on to get his master's and PhD here at the University of Colorado in Boulder.
Yeah. What? What?
This is where he began developing the navigation methods that would one day guide spacecraft across millions of miles of deep space. So welcome back to our campus.
All right.
At NASA's Jet Propulsion Laboratory, Dr. Jha played a crucial role in some of the most iconic Mars missions of our time: Mars Global Surveyor, Mars Odyssey, the Mars Exploration Rover, and the Mars Reconnaissance Orbiter. But it was after NASA and Dr. Jha that Dr. Jha turned his attention to what is often called space junk. Today, thousands of satellites and more than 100 million fragments of debris orbit our planet at high velocity. Each piece, whether the size of a school bus or a fleck of paint, has the potential to damage spacecraft, disrupt communications, or threaten astronauts. Dr. Jha sees this as an existential issue for how humanity stewards space environment. He then went on to co-found Privateer Space with Apple co-founder.
This guy named Woz.
Wozniak, in an effort to map and monitor orbital debris in real time and make space data transparent and accessible. He also established Gaiaverse and Moriba Jha Universals, ventures that bring decision intelligence to global challenges, linking planetary stewardship with space stewardship. In 2022, he was awarded the MacArthur Fellowship, recognizing both his scientific breakthroughs and his moral imagination. He has been elected a Fellow of the American Astronautical Society, International Association for the Advancement of Space Safety, the Royal Astronomical Society, the Air Force Research Laboratory. He's a sought-after voice in policy circles, has testified before Congress, and served as part of U.S. delegations to the United Nations. Dr. Jha is the co-editor of the IAA and Elsevier Acta Astronautica journal. But and his work has been featured even for a broader audience in Nature, National Geographic, Popular Science, the BBC, and NPR. Now, I could go on listing more of his incredible accomplishments, but truly there are far too many to cover tonight. His resume is nothing short of extraordinary. And I expressed that earlier too. I'm just in awe. So what matters most, however, is the clarity and urgency of his message, that our future, both here on Earth and beyond it, depends on how wisely we manage our shared space environment. He reminds us that the space environment is not infinite and invulnerable. It is, in fact, a commons, fragile, shared, and essential to human life. His work calls us to take responsibility not only for our planet, but for the environment beyond it. Tonight, we are fortunate to hear from someone who blends scientific brilliance with ethical imagination. Someone who challenges us to think about engineering not just as a tool for innovation, but as a practice of stewardship. So please join me in giving a warm welcome to our guest, Dr. Moriba Jha.
Thank you so much. Thank you. Aloha nui loa, everybody. Can everybody hear me? Yes? Excellent. How about back there? Yeah? Okay, cool. Yeah, so I guess first and foremost, I want to say thank you for having me in your presence this evening. It's good to be back. I had an amazing time going to school here, and my son just graduated from engineering physics in May, and he's in Berkeley doing all sorts of theoretical physics things. But in any case, CU Boulder means a lot to me personally, and so I appreciate being with you. When I heard about the opportunity to come here and speak about responsible engineering, it is very near and dear to my heart. I see a lot of engineers focused on just cranking out solutions, but then it's like, well, so what, and who does that impact? Who does that affect? One of the things that Anya so graciously said about my past is I am into this thing called space junk, and unfortunately there's a lot of it. I wish there was actually more time for the lecture. I probably have more slides than minutes to talk, but I'm going to go through them, some of them more quickly than the rest. But this is just to kick this off in terms of responsible engineering. So in 1957, we, humanity, launched Sputnik. That was a feat in and of itself. Ever since then, we've been launching these robots in the sky that we call satellites that help us do lots of things, send us internet, communication, position, navigation, and timing. All sorts of infrastructure is increasingly more and more space-based. So we went from launching Sputnik in 1957, and I didn't know about this problem until I left NASA and went to Maui. So where's Maui, some of you may ask? Well, it's here in the middle of the Pacific. I still have a home there. And on the island of Maui, if we zoom in here a little bit, we're going to see the top of Mount Haleakala. There's going to be this facility. And this is where the Space Force and University of Hawaii have a set of telescopes. This right here is the round thing is like a 3.6 meter adaptive optics system that can do like daylight imaging. But it was through these telescopes on top of Mount Haleakala that when I looked up at the skies, all of a sudden I started seeing more and more of these dots that weren't necessarily all labeled, by the way. Right now, we're tracking about 50,000 human-made objects in Earth orbit. All the dots that you see are fragments or a whole dead satellite or these sorts of things. And the blue things are working, everything else is junk. So we have about 11,000 working satellites. 75 to 80% of all working satellites belong to Elon Musk and SpaceX. He's launching 60 of these every 2 to 3 weeks. While you're sleeping and snoozing, satellites are going up, and each one of these is like a single-use plastic, because it takes a really long time for those things to decay and burn up in the atmosphere if they're in low Earth orbit, and if they're far away from the planet, then they never come back. So there's that. So we're great at engineering stuff. We engineered plastic. That's been useful, right? It has helped us preserve things, help us protect us from diseases and that sort of stuff, but it also has a detriment. Satellites are very useful. We need to still use them, right? We need to get data and information from them, but there's a consequence depending on how we engineer things. So today we're going to talk about that a little bit, and so I'm going to less wow you with that sort of thing, and let's go to this, and let's proceed. Lots of stuff happening on the planet. Dumpster fires everywhere on the planet, right? We can't outrun the fires. We can't outswim the floods. We can't outfast famine. And the thing is that we have forgotten about the interconnectedness of all things. We've forgotten about the interconnectedness of all things, and we have forgotten about our intergenerational contract of stewardship with the planet. So in engineering education, we often frame this stuff as this pursuit of certainty, precision, optimization, all nice things. But this thing that we call certainty, it may be a bit brittle. Certainly, when we ignore ignorance, and we'll get into this more in this lecture, when we ignore ignorance, when we oversimplify the complexity, because people, let's face it, we all like simple answers, right? Bad things can happen as a consequence. One of the things that I hope that you get from this exchange, even though it's called a lecture, I don't think of myself as a lecturer. I think of myself as just a dude that has conversations. So I'm going to be a dude that has conversations. And we're going to have some of those, hopefully. I'm hoping that we leave this mutual conversation with some idea of humility, admitting our limits, finding ways to preserve doubt, and confronting unintended consequences. And that's a key thing, unintended consequences. Let me give you an example of that really quick. So a couple years ago, I was doing a photo shoot with this guy out in the Mojave Desert. And his name's Stephen Lyons. He's a world-known photographer. He spent lots of time in Africa photographing wildlife. And one of the things that he said that he did, which was amazing, was he showed me this picture of this rhino. And he said, I spent 2 weeks out in the African bush trying to find a way, without any sort of shielding of trees or anything, it took me 2 weeks to be able to get close enough to this rhino for me to take this amazing picture. And the reason I wanted to take that picture is because I wanted to show the world how beautiful rhinos are. And so it took me this time to get close enough to take the picture. 4 days later, rhino is chopped up by poachers. So a question is this. When he befriended this rhino, did that lower the rhino's defenses, and it's like, oh, sounds like two-legged people are cool because they just have this thing that makes a click and everything works out at the end, except not so much. And the thing is, who knows, right? I mean, clearly I'm not somebody, I can't channel the rhino to know what the hell the rhino was thinking, but at the same time, one has to ask the question, what are the unintended consequences of wanting to do good things? So it's not just about doing good stuff, it's taking the time to not be so arrogant as to think that you just know all the ramifications and consequences. And the thing is, you can't. So you have to make some decisions in that uncertainty, but taking the time to think about unintended consequences is critical. So there's this thing called maximum entropy. We'll chat about that here a little bit. This other guy, Karl Popper, he talks about falsifiability. We'll get into that a little bit as well. But the thing is, every equation for an engineer impacts lives. And the question is not just does it work, but who's helped and who's harmed in that process. So Karl Popper is this philosopher, and his kind of one of the things that he's known for is this idea of falsifiability, which is, in his mind, it's the demarcation between science and pseudoscience or non-science, right? And as to say, in order for this to be science, it can only be science if there exists evidence that can refute the hypothesis. If the hypothesis, if there's, so one of the things I tell my students is if you want to know something, you have to measure it, okay? You can't know the unmeasurable. So the thing is, if there is a hypothesis that you want to entertain and there's no way in hell that that thing can be measured in any way, best not to even entertain the hypothesis. Because you want to have evidence that can possibly refute it, okay? So knowledge grows by removing ignorance, not by proving certainty. The models have to remain vulnerable to being refuted. And responsibility in engineering is building systems that can fail transparently. So the danger comes when ignorance is hidden, responsibility is hidden. So anybody here familiar with black swan events? Anybody heard of a black swan? Okay. So what are some characteristics of black swan events? Okay, here's the thing. Okay, cool. Go ahead, man. What's your name?
Distan.
What?
Distan.
Distan? Okay.
Unpredictable, beyond human control.
Okay. Sorry, so you said unpredictable, beyond human control. You want to be on the mic? What do you think?
Wouldn't mind.
Wouldn't mind. Okay. Distan is brave, courageous, doesn't mind being on the mic. Let's go,
Black
brother.
swan events are unpredictable. They're beyond human control. Humans can only anticipate, but they cannot really prevent them. They can prepare themselves, but they cannot fully combat them.
Okay. I like what you said, Distan. Cool. By the way, this is a safe space. You want to say something that's just off of whatever part of your mind, say it. You're not going to get ridiculed. We're having a conversation. So I want you to remove the fear. It's going to be okay. So here's the thing, right? So black swan events are these things that supposedly unpredictable, and in hindsight, it's duh. Okay? Unpredictable at first, but in hindsight, it's a duh thing. And the thing is, people might attribute these things to randomness, but I don't. In fact, between you and I, I'm not a believer in randomness. I think randomness is a thing that we made up, but it's useful. But that's like a separate talk. But when I look at these events, like the Titanic, like the Challenger, somebody asked me, they said, well, we're talking about the Titanic, and they're like, you know what? That thing, it was a tragedy because of that pesky iceberg. I'm like, you know what? It wasn't the iceberg that did it. The iceberg is the random thing. The thing that did it was absence of sufficient lifeboats. It's that systematic thing. It's the thing that comes from hubris. It's the thing that says, oh, improbable equals impossible. And when people say that, bad things happen as a consequence. Okay? People use probability a lot. Probability of a collision, probability that the Titanic's going to sink, probability of the probability kind of thing. And so, again, what's improbable goes as negligible. Probability of the Titanic sinking, oh, that's pretty low, so ignore it. So when I say in uncertainty quantification, we have like two types of uncertainty. Aleatory is like due to randomness, and epistemic is due to like systematic things, or let's say ignorance. And so, like I said, for me, black swan events aren't about the random piece. It's about the systematic thing that, because it seemed like it was improbable, it wasn't something to consider. Probability tends to minimize risk over average outcomes, okay? Probability tends to minimize risk over average outcomes. Probability makes lots of assumptions that, in many cases, get violated, but we utilize this anyway, and we're going to go a little bit deeper into that. So this idea of maximum entropy. So here we have this kind of equation on top. This entropy has something to do with the sum of, say we have some random variable x. So basically, it's summing over the probability that that thing has an outcome times the log of the probability of that outcome, and it's the negative of that. So entropy, think of entropy in this sense as uncertainty, right? And so this person, James, his principle is to say we should be trying as much as possible to represent things by embracing and modeling that maximum entropy, by embracing and modeling our ignorance, being honest about it. So the thing is, the implication for responsibility is that models that minimize entropy pretend that they know more than they do, and we're going to talk about that. Maximum entropy preserves humility. The best path to truth is through ignorance. The thing is, uncertainty feels uncomfortable. And we bring our prejudice all the time to collapse the uncertainty because we want to make decisions and we want to simplify things, even if the data don't really allow us to extend that. Okay? So just going through this idea of entropy again, one of the things that we can do to try to optimize this is we can construct this thing called a Lagrangian. The first term is the entropy that we talked about earlier. The second term is, well, probabilities assume, the law of total probability says everything has to sum to 1. The universe of discourse, which is everything that I care about, I know the distribution of outcomes. I know that distribution perfectly. I have a probability density or probability mass function or something like that. I know the distribution. I know how probability is distributed amongst all the possible outcomes. That totality is 1. And the probability that any given outcome happens is going to be greater than or equal to 0. And the other thing, too, is that in this universe of discourse, if I have a bunch of sets in that universe of discourse, and these sets are mutually exclusive, then the probability is the sum of the individual probabilities of those sets occurring. The union of those is going to be the sum of that. So that's what probability assumes. And the question is, under which conditions do we actually have all that stuff? Probability alone can tempt us to overfit and collapse that uncertainty, and we're going to see that in some examples. And again, the maximum entropy is trying to help us remain agnostic where knowledge is missing. Okay? So we're going to get into this. Everybody here, of course, has heard of Occam's razor. And the thing is, I think it's been widely misinterpreted. Because I think, at parties, when I talk to people about Occam's razor, because, that's what they talk to me at parties about, Occam's razor, because that's a cool thing to chat about. It's like, okay, given the evidence and things that explain it, the simplest one tends to be the one that you should go for. And I don't think it's about the simplicity. I think it's more about the one that makes the least amount of assumptions. The explanation that assumes the least or doesn't assume things beyond what's there is the one that you should go for. And so that's my interpretation in terms of entropy and Occam's razor, is simplicity in this frame is simplicity in terms of like the assumptions, not the actual hypothesis itself. Don't assume more than the evidence supports. Here we go. Let's try out Occam's razor. Do you still have the microphone, or did I take it back? Man, okay, I put it on the table. By the way, I'm not accusing you of keeping the microphone. I couldn't find it. He's looking at me kind of like, hey man, what are you trying to say about me and microphones? I don't know, nothing. So here we go. We're in this building, it has windows. We hear tires screeching. We go out to the window, see what happened. There's a car, door open. Driver is shouting some stuff because we can't hear it. We can't hear the driver scream, but we heard the screeching tires somehow through the window. There's a cyclist on the ground and a bicycle laying on the ground. Question to you is, what happened? Anybody? Answer me! No, I'm joking. Okay, who said that? So what's your name, sir?
Robin.
Robin. So Robin says car hit the bike. Booyah. Anybody else? What's that? Biker hit the car. Okay. I mean, I hear some chuckling. Okay, go ahead.
There was an accident.
There's no accident?
There was an accident.
There was?
Yeah.
Okay, and that's it?
No blame.
No blame? So, but what happened? You said there was an accident.
Yeah.
Okay, what was the accident?
Between the car and the biker, but we didn't see who.
Okay, right. So I'm asking you, can you tell me like what you think happened?
He'd be assuming at that point.
Right. Okay, anybody else? So the point is this, right? Most people, Robin, okay? Most people are going to be like Robin, which, by the way, I'm not saying that this is a bad thing, but the tendency is to slam the uncertainty, make some assumptions, and it's like, well, why the hell was the car actually out here anyway, right? One's supposed to be driving down here. Thing is, the assumption is that the car hit the driver. And what I'm telling you is that there's not enough evidence to collapse that into that binary car hit the driver kind of thing. That's a prejudice that we bring to the table because we don't like to sit with uncertainty. And when somebody says what happened, we feel this urge, oh, well, I need to come up with an answer, and it has to be a binary answer. It has to be unique. It can't be things that are in tension with each other. It can't be conflicting evidence or conflicting hypotheses. So on one thing is, nobody hit anybody. The biker just happened to fall. The car stopped because it's a good Samaritan wanted to help out the biker. That's a possibility. Like, right? It's possible. But the thing is, we don't even allow that hypothesis to be on the table because we don't let it. And that's dangerous. So one of the things that Rudolf Emil Kalman, the co-inventor of the Kalman filter, was after was this idea of prejudice-free inference. Basically, the whole thing was, he was at some Kyoto Prize, I think in '84. He was saying, is a model truly data-driven, or is it just reflecting the bias of, artifact of the person doing the whole filtering? And so that's something that stuck with me throughout my career, is what does it mean to be prejudice-free? Well, thing is, if you're using probability and you're using Bayesian inference, then you have to have a prior belief coming into it. That's a requirement. You have to have a prior. What is that prior belief? How sure are you of it? What happens when you come in with a prior that's biased? Well, the posterior is going to be conditioned on that. So now you have a biased posterior. You can't get away from that. So what does prejudice-free mean? Well, to me, it means either you assume nothing or you assume everything. So Rudolph Emil Kalman was able to operationalize Bayesian inference. And I say prejudiced in that sense that you have to have some prior, okay? The thing is, if you have too much faith in the prior, well, then you may be clinging to assumptions. You may be confirmation biased, right? At some point, your belief can become so tight that then you have confirmation bias, or what I call belief inertia. And at that point, even if you get evidence that might refute your belief, that's an outlier. That's something that you disregard, something that you sweep under the rug. But if you put too much faith in the data, then you may just be chasing the noise, overreacting to fluctuations and that sort of stuff. So responsibility here means maintaining an honest, transparent balance between the two. One of the things that Kalman warned about, he said, system identification from noisy data is one of the most urgent, unsolved scientific problems. Humility means acknowledging what the data cannot tell us. Prejudice-free inference is treating ignorance honestly and not trying to fill in gaps with our assumptions, not trying to just go directly and say, hey, the car hit the biker sort of thing. And it's not weakness. It's just the responsible thing to do. So one of the things that I've been exploring as a way to model ignorance is possibility theory. And we talked about probabilities a little bit. We said it's additive, and it goes between 0 and 1. It requires this precise knowledge of the underlying distributions. It implies knowledge of joint distributions. The tails of events, by definition, are low probability and, unfortunately, treated as things that are negligible. Whereas in possibility, and we're going to get a little bit deeper into this, when I say ordinal measure, I mean we're talking about degrees of possibility. And something that has a possibility, in possibility theory, things that have a possibility of 1 are things that have not been rejected by the evidence. So it's fully plausible because nothing rejects it from being. And a possibility of 0 means that you have evidence that fully rejects it from being possible. One of the things that I like in terms of inference is I'm into abductive inference. And I believe that I have some slides talking about abductive inference. So yeah, so just more here on possibility distributions. Again, we have some Posse distribution, pi that basically maps possibilities between 0 and 1. It's not frequency, it's not likelihood. I can't tell you, hey, this is more likely than that. I can tell you what's more plausible in terms of there's more evidence that rejects this than that. But I can't say anything about the likelihood of its occurrence, okay? It also means that in terms of ordinal semantics, I can tell you what's more plausible than other things based on what has been rejected or not. But I can't tell you the likelihood, okay? Core operators in possibility theory for joint possibility, the intersection. So this is where we say this and that. So it uses a min operator because we're saying the most conservative thing that we can say if we say the intersection between these two things is where's their consensus. I can only talk about the thing that is the least plausible, is the more conservative thing. Marginalization, we use a supremum between these sorts of things. And it just means that we're looking at the max of this. Then we have this conditioning of the possibility distribution that's just proportional to this intersection between some marginal and some conditional possibility distribution. And then the cool thing is that there's this thing called necessity. So in possibility theory, if I say I'm looking at event A may be satellite, a Starlink satellite and an Iridium satellite may collide in space. Let's say that's what I care about. That's event A. If I have no evidence that rejects that from happening, the possibility is 1. Necessity then says, well, what is the possibility of everything that's not the collision? The possibility of the things not colliding. And if I don't have evidence that rejects that, then you can see that when I do 1 minus what's not the collision, the necessity in that case would go to 0. Because if nothing rejects the thing not colliding, that's 1. 1 minus 1, 0. So the necessity would be 0. So what that means is that I can have a possibility distribution, and I can say this is fully plausible, but it's not necessary to explain the evidence. That means that I can't have full confidence that this thing is going to happen. However, if I do have evidence that fully rejects that the thing won't collide, then I have a lot of confidence that the thing will collide. So necessity is almost like a second order kind of uncertainty when it comes to possibilities. I talked to you about abduction. It ain't me going and trying to like kidnap people. That's not what I'm talking about here, okay? Just letting people know. When I talk about abduction, think of it kind of like, okay, let me say this. Whenever people here take an exam, do you like to be asked to give the answer directly, or would you rather have multiple choice? What's that? Okay, what's your name? Bella. Who agrees with Bella? Multiple choice tests are, thank you. I was having trouble seeing people. It's getting dark. Okay, multiple choice tests. Let me say this, right? Who knows exactly where Abraham Lincoln was born? Okay, don't say it. Okay? Somebody knows. So most people here don't know. What's that? I'm not sure I know. Okay. Please don't say it. So the thing is, most people here have no clue. And of course, you can go into your phone, you can Google it, and all of a sudden it's like, oh, I know it, right? The thing is, most people here have no clue. If I give you a multiple choice exam and I say, A, Dallas, Texas, B, San Francisco, California, C, Richmond, Virginia, D, Louisville, Kentucky, E, Hodgenville, Kentucky, what are people going to say then? What can I eliminate? Okay, I can eliminate Texas. I can eliminate San Francisco. What else can I eliminate? What's that? I can eliminate Kentucky? Okay. What's your name? Ian. Okay, Ian. We're going to come back to you, Ian. What else can I eliminate? Virginia. So here's the thing. So he was born in Kentucky someplace. As somebody who's amazing at predicting, I could tell you knew that was coming when I said, hold on, right? Okay, good. So the thing is, we can use evidence to reject stuff. Evidence is very good at rejecting things. Evidence is great at telling us what the wrong answer is. When I do abductive inference, I see myself, and by the way, it also tells you where else you need to collect different evidence to further reject the wrong answer. I think of myself as a sculptor of knowledge. My block of marble is ignorance. And just like a refrigerator doesn't directly cool, a refrigerator removes heat. I'm not interested in directly finding the truth. I'm interested in removing ignorance. And I hope that by removing more and more ignorance, I can arrive at the trapped statue of David inside. That's what I'm after, okay? That's what abduction is all about. This guy, Sherlock Holmes, everybody's heard of good old Holmes. You know, what's up, Holmes? No, maybe that's a different Holmes. So, so Sherlock Holmes applied this sort of thing, right? It's like, and one of the things he's known to say is that when you've eliminated the impossible, whatever remains, however improbable, must be the truth. Booyah, okay? So it's all about being epistemically humble. So I talked about this, the ignorance as the marble, data as the chisel. And abduction risks overconfidence, sculpting too quickly. We can use Popper's falsifiability to say, I'm only going to remove the thing that has been shown to be rejected by the evidence. And the thing is, machines have to learn that same humility. That's one of the things in AI that I'm working on is how can we embed this epistemic humility within the AI? Because how many times have you gone to GPT or whatever it is? You can ask anything you want. How many times did Jesus Christ, breathe? You'll get some answer, right? It's like the thing knows everything, the unknowable. That's BS. So AI is a collaborator, but one that needs to be infused with the humility to respect the plurality of things that might even be in conflict or tension with each other. Talked about the black swans. I'm going to move forward from that because I think we get it. But here's the thing, right? There's a devil's advocate to this, which is, and this is what people always hit me up with the cost. What's the cost of being epistemically humble? What's the cost of maintaining all these possibilities and hypotheses, right? And so the traditional risk model is, risk is the product of likelihood and consequence. So the thing is, in practice, likelihood is underestimated because you think, okay, the tails of the thing and you don't look at the systematic things, the worst case scenarios that can stack up against you. And then the consequences are usually ignored until the catastrophe happens. So the thing is, short-term savings can end up with long-term catastrophe. Likelihood also focuses on this aleatory or random variation. The systematic ignorance, the epistemic uncertainty tends to be left out. And here's the other thing that I wanted to say about aleatory versus epistemic uncertainty. And this is what I posit. This is just my own opinion. My own opinion is that if something is inherently random, if the uncertainty in something is inherently random, then there's no data or measurement that's going to inform you more about this thing by definition. There's no additional piece of information that's going to let you know more about this thing if its uncertainty has been reduced to what is just purely random. To me, that's the floor of learning. And anytime I'm doing inference, if data tells me something more about the thing I care about, then that uncertainty was epistemic. It wasn't aleatory in my book. It was me removing ignorance, not knowing more about the randomness of the thing. The responsible thing is, again, not collapsing epistemic uncertainty into false precision. And black swans, in my opinion, don't reveal nature's randomness but our ignorance. I believe that we live in a non-random universe, but we're just ignorant about almost everything. So one of the things that I put together in modeling this ignorance, I've put together over the past 6 to 10 years, I've been going deeper into this idea of possibility theory, and I put together this kind of engine. I have this thing called an epistemic support point filter, which we'll talk about here a little bit. I have this possibilistic hierarchical mixture of experts that lets me weigh explanations, not forcing single winners. I have this thing called socio-technical configuration analysis. It comes from social science. Because the other thing that I've discovered in this whole thing about trying to understand what's in space, all these debris, understanding this, people want to study that from a purely physics perspective. Here are the orbits, this is what the sensors are telling me, but it's like the places where we put the stuff, some of it is driven, right? Science reasons, that sort of stuff, cool. But what we launch, how we launch the stuff, well, policy and international laws drive behavior. Culture drives behavior. I can tell you right now that the way SpaceX operates Starlink satellites is different than how Iridium operates their satellites. It's because the company cultures are different, and that becomes manifest in how they operate their satellite and the behavior of stuff. So the behavior of stuff in space isn't just Mother Nature, natural causes, it's human-driven. And to neglect that is to not be humble and respect that ignorance. So socio-technical configuration analysis is something that comes from social science that says, here's a way to fuse technical inputs with social inputs so that we can get a better picture of interdependencies and perhaps even better predictive models to understand these behaviors. And then I came up with this thing called this epistemic trust kernel to model not just data, but how we should trust the source of those. So all this thing together is like this maximum entropy abductive inference engine, okay? So just looking at the epistemic support point filter, again, I was after something that was more towards prejudice-free. I don't have to have these prior assumptions. I don't want to assume the law of total probability where I know all the possible outcomes, that everything is additive, that everything is independent and identically distributed, and that I know what the distributions are and all that sort of stuff. So I developed this thing called the ESPF. So it's non-Bayesian, kind of by definition. It's an alternative. Some key features is that it uses the possibility theory. It maintains this uncertainty without prematurely collapsing it. I don't immediately assume the car hit the biker sort of thing. And I want to use this to see how it handles ambiguity, biases, information loss, that sort of stuff. We start with a region. So here's one of the things that I can say, right? Because people are like, okay, if you don't have a prior, how the hell do you start this thing? Good question. Let's say I'm trying to track something in space. I have a sensor. It's a radar. I get a detection of this object. What do I know? If I have a radar and it detects the satellite, what's known in my universe? What?
The position of the satellite.
Okay. So, right. So what's your name again? Uriel. So one thing that I know for sure is I know everywhere else in the universe that that object isn't. So I can use the evidence to reject the possibility of it existing anywhere outside of the field of regard of my radar. Is that a large region of ambiguity? Sure. It's a lot smaller than the rest of the universe, and I don't have to make assumptions about likelihoods or probabilities or any of that stuff. So the way that we kick this epistemic support point filter out is we say, there are some things that I can assume given that there are places that I can reject as the thing that I'm interested in knowing, where that resides, how that lives, how that breathes, so on and so forth. I am then going to create a sparse grid approximation over that region, and then I'm going to, in my case, because I'm looking at things that are part of a dynamical system, I can take these support points, these sparse grid approximation of this region of ignorance, I can propagate that forward in time. I have a relationship between my measurements and where the objects are located, and then I can come up with a mechanism to update my beliefs conditioned on the compatibility that exists between these measurements and where I think the thing is. I can then, in possibility theory, there's a type of aggregation called a Choquet integral, which you see right here. And basically, it lets you apply possibility distributions to the combinations of subsets. Let me give you an example. So it's like if I have a radar and a telescope and a space-based telescope, the capacity function would say, yeah, the possibility of the radar alone, what that adds in terms of information is going to be less than the radar plus the telescope, and is going to be less than the radar plus the telescope plus the space-based sort of thing. So it's a way to bring in different opinions and consider all of these things and weight them in a way that to fuse all this. From that, I can, Choquet integral, I can fuse these things, I can get this updated state, I pick the mode, and the mode is just the place of the highest possibility, not the highest likelihood. And the cool thing is, I don't have to prematurely collapse any sort of uncertainty, and I can be humble about what it is that I'm trying to infer. So probability asks, what's the average outcome? This filter asks what possibilities are still standing, which things stand the test of the evidence. So to evaluate this sort of thing under some real-world situations, I looked at things in low Earth orbit, things in geostationary orbit, and I compared it to this thing called the unscented Kalman filter, which is something that lots of people use. These are just some assumptions that I'm making on this object in the low Earth orbit and in geo. And one of the things that I wanted to see is, could this thing handle biases, and if, unbeknownst to me, if the area of some object changes and that sort of thing. These are just like some initial conditions. And, for the Leo case, I just said, hey, I have 3 sensors. I'm going to observe the thing over 6 days. I got a measurement once a minute while the thing's in the field of view. I have a 10 arc second bias in one of my sensors, which I'm not going to let the filter know about. It's an unknown bias. And then in the geo case, I basically have some tracking sessions with measurements every 15 seconds, and then I have the thing changes its cross-sectional area, and I don't tell the filter of that stuff either. And so the objective here is just to compare these things with each other, numerical accuracy, and then some indicators with this epistemic support point filter, like necessity, which I talked about before. We'll talk about surprisal and entropy. So this is, so at first, this is like unbiased data. I just want to see what happens with unbiased data. And the stuff on the left is the unscented Kalman filter, and the stuff on the right is the epistemic support point filter. Remember I said the necessity is 1 minus the possibility of everything else. So here, with the unscented Kalman filter, the necessity is going between 0 and 1. It's saying, yeah, I believe that your state is necessary, I don't believe it's necessary, or it's completely unnecessary to support the evidence, so on and so forth. The bounds, the red bounds there is it's called the innovations covariance. It's the belief that the filter has in where that state of the satellite is in measurement space augmented by the measurement noise. And the filter is going to believe that no matter what, is just because of an algorithm. It's not because it actually knows anything. It's just proceeding. Here on the right, the actual residual, so the difference between what I predict and what I observe, I have, and I know you can't see the numbers up there. Actually, what's your name back there? Sir, with the glasses on? What's that? Felix? Cover your left eye and read. No, I'm just joking. So here's the thing. So you won't be able to see that, but I'll show you the numbers of slightly better than the UKF. But the cool thing is that this necessity is actually going from 0.996 to 1. So the thing is, I see that the state that's being inferred from this kind of abductive inference engine, it's faithful to what is true. I compute the surprise, how surprised are my support points with every measurement. So high surprisal means an inconsistency between what I predict and what I observe. So that surprisal flattens out at 0 quickly. This right here is the entropy as a function of time. And the fact that it's negative is good. It's basically saying that we're looking at, because this is the negative log of the determinant of the possibility. So think of this as like the spread of the support points. This kernel radius is just saying how wide this ambiguity region that I defined at first, it's basically becoming less and less ambiguous, which is good. Now, I put in the bias just to see what would happen, and the UKF doesn't like that so much. And you can see that the bounds are still what they were before, like I had told you, because it doesn't know about the bias. And you can see the residuals that are way outside its confidence. So the UKF is lying to you in the sense it's saying, hey, I believe the thing is here, but you can see the differences between what it predicts and what it's observing. The epistemic support point filter, the bias occurs, and the thing is, it's handling it. It actually recovers quite well in the presence of the bias, and you can kind of see, just based on surprisal and necessity, it's like an indicator to you that there's something that you didn't take into account, which is kind of what you'd like to see. And then the one for this geostationary satellite, it changed area twice, and the UKF has no clue. It's like, oh, it's like another day in Boulder, Colorado, man. Everything's okay. Those aren't the droids you're looking for. It's cool. But these measures of necessity and surprisal, specifically the surprisal in this, give us indications of this change in area. So yeah, so that's kind of a cool thing. The necessity really helps understanding some of these things, keeping myself honest. I use this Karl Popper's falsifiability kind of thing based on measures of surprisal, and is just showing you how many things are being rejected. But I can make more support. I do make more support points after I update my my state. And this is just showing you in terms of like compatibility between measurements and where I think the object is. The things that don't make sense drop out, and the ones that do, hang in there. And then this is just the performance between these things for all these cases. So yeah, so this is something that I've developed recently and will continue to use it. And I'm hoping that other people start looking at this as an alternative as well. And then I told you that I developed these things like the possibilistic hierarchical mixture of experts, this socio-technical configuration analysis, and this thing called an epistemic trust kernel, which basically is a way to try to find ways to work with people across the globe in ways that they're privacy-preserving measures, and what are ways in which we can trust each other so we don't basically lead to an armed conflict in outer space. Focusing back on responsibility here, engineering is never neutral. So every design encodes bias. So the question is not whether bias exists, but what bias are you choosing? Because you can't get away from it. And even though your mathematics can be prejudice-free, inference without distortion, maximum entropy, falsifiability, but your purpose is never neutral. And so your responsibility as engineers is to choose your bias deliberately and think about the unintended consequences of what you're doing. My hope is that you focus on generating solutions that are regenerative, restorative, and socially just. Not extraction, not exploitation. I'd love for you to embrace that. Humility beyond the equation. So resist the temptation to assume beyond the evidence. Preserve the uncertainty for as long as you can. No solution is unconditionally good. Every design has ripple effects. And again, the hard questions are, who benefits from this? Who bears the hidden cost? Is there anybody who's being oppressed as a consequence of the thing that I'm developing? Is there anybody who's suffering as a consequence of this sort of stuff, right? If you can think about all those things and make informed choices, then I think the world can be a better place. And these are some unintended consequences of some of our engineering. You know, DDT, miracle pesticide, but not so good for the extinction of some species. Social media, everybody thought, hey, this is going to bring the world together. In so many ways it does, but in other ways, not so much. Graveyard orbits, basically orbital landfill equivalents. So good intentions, not necessarily good consequences. So I'm asking you to think about discernment, about restoration instead of domination, responsibility, not certainty, embrace the uncertainty. And I guess closing challenge here is, can you do that? Can you do that in your career, in your jobs? Can you bring yourselves to start thinking in these ways? So I like this quote from Bertrand Russell, right? It's so evident. Thank you very much.
Are you ready to take some questions?
Yeah.
All right. Do we have any questions? I think we have a couple minutes here. All right. Where should I go first?
Hi there, I'm Bella again. I am one of Anya's students, actually, and I was just wondering if you think that you're talking a lot about like removing ignorance instead of making assumptions. And do you think that at least in part removing ignorance is adding knowledge? I was kind of thinking about like Plato's Apology and stuff like that, and how he says like me sitting here saying that I know nothing makes me the wisest person here. So do you think that in some way, removing ignorance is still adding knowledge?
It is, 100%. Yeah.
Hey, Professor Jar. I'm Ashish. I'm a former student of Anya and Professor Siebert back there. I have a question or a follow-up question on STCA, the socio-technical configuration analysis.
Yeah.
So, like, the thing about black swan problems where engineers kind of mispresume improbable to be irrelevant. And, like, the power structures that engineering occurs under in practice. So, like, you know, engineering incentive from capital, you have funding that you're beholden to, you have investors, and that kind of like financial incentive. When McDonnell Douglas took over Boeing and their engineering culture was replaced with McDonnell Douglas's management culture, and then you have like doors flying off of planes, or you have a single guy shooting up a bunch of useful but single-use crap into the atmosphere. I'm wondering, like, do you think that there's a distinction to be made between fault, blame, and responsibility in solving engineering challenges, either self-inflicted or pre-existing? And then are there ways to bake accountability into these like hierarchical structures that facilitate engineering in practice?
Yeah, cool. So in the question of fault, blame, and accountability, yeah, I think there's ways to define that. There's certainly ways to define it if you're a lawyer. You know, I'm not one and I don't play one on TV, but yes, I believe that there are ways to define that even within an organization. And I had a meeting with a group of students earlier where we had some of these conversations. And one of the things that I said is that in the organizations where I've worked for and in, I've had the experience of being in organizations that have an ethics committee and ones that don't. And the thing is, I would suggest to you, any job that you take, ask that potential employer, do they have an ethics committee that's part of their organization? And if not, that's certainly something that you should encourage for it to exist. And if an ethics committee exists, then you should wonder, what is the representation on that ethics committee? Okay? Are there entry-level engineers, such as yourselves or whatever, that are represented on that? And whenever the company or the organization has all-hands meetings, then the ethics committee should be an agenda item. That's what I think. But I don't know why I did that, I just wanted. All right.
Hello, Dr. Ja. Thank you so much for this wonderful talk. Thank you so much.
Yeah.
My question for you today is, as engineers and future leaders, there comes a time when we have to make decisions, even though there is uncertainty in the decisions we make.
In that case, the car hit the biker. I'm just... No, go ahead, man, sorry.
Exactly. I was just wondering, how do we reconcile how much uncertainty is acceptable when we make those kind of decisions? Because at some point, we have to make a decision.
That one's really hard. There are times in which you do have to make a decision and you're forced by time to do that. And all I can say is that when you have to make that decision, my hope is that you've done everything that you can to be the best steward, the most responsible person in managing that uncertainty. But at some point, it just becomes a thing of like tradecraft or gut. I'm going to give you an example real quick. There was a time when I was working for the Mars Odyssey mission, and I was a spacecraft navigator that was, with JPL, but I was at Littleton. Because here's the thing, I accepted a job at JPL after my master's degree here, but I got accepted into the PhD program here. I passed my quals, and my employer said, well, the job is here now, or nunca, or never. And so I said, okay, I'm gonna go to JPL. But then I talked to my boss and I said, hey, this Mars Odyssey mission that I'm on, what if I volunteer to take nights, weekends, and holidays, and I'll do it from Littleton, just in case something happens at JPL, you have an extra navigator at Littleton that could do something. And they said, oh, that's a great idea. So that during the daytime, I could take classes here, and at night, I was working the mission. On one of these evenings, the thing's in aerobraking, so part of it is going through the atmosphere, and the other part is like way out of the atmosphere as a way to bleed out energy from the orbit instead of having to use propellant. And typically, the thing would go, it would veer off from Earth like 30 minutes around the time of closest approach to go through the atmosphere, no contact. Then automatically when it popped out of the atmosphere, it was supposed to reorient itself and resume tracking. And based on the tracking data before and after, that was what you needed in order to see, did the thing go in too deep, too shallow? I need to make some decisions. I only had 3 hours, up to 3 hours after the thing came out of the atmosphere to deliver an orbit to the project, to update, to send commands up to the satellite to update the knowledge. And I wasn't getting any data, no data, no data. Finally, I got like 15 measurements, man. And it was time crunching, it's like 2 hours and like 50 minutes, 15 measurements. Every time I tried to fit the data, the solution was jumping, it wasn't stable, it was unstable. And I'm like, okay, what could go wrong? Multi-million-dollar thing. I'm just some dude in my 20s, like cool, great responsibility to have. And the thing is, I applied the teachings that I had here from CU. Of course, that's always going to be the thing that you want to say, right? And I try to be kind of rigorous with my assumptions and these sorts of things. And the thing is, I just had to make a best estimate at that point. And I was scared crapless. And it worked out. But yes, there are times when you need to make a decision and you're forced to do it. And that's when you just have to be, not only just trust yourself, but have the grace to know that you did the best that you could under those situations and conditions. So.
Okay, we have time for a few more questions. Oh.
Thank you. Thank you for the talk. That was illuminating. With respect to the possibility theory, that framework that you developed, and you talk about ranking plausibilities rather than talking about particular probabilities. This is, I mean, just from scratch as a noob, how would you distinguish estimation of plausibility in the absence of information and the uncertainties that you talked about, and how is that distinguished from assigning probabilities? Again, in the absence of information. So basically, I'm asking, have you not just shifted our ignorance in terms of estimating probabilities to our ignorance in terms of assigning values to different plausible outcomes?
So I think that's a great question. And you said, how do I do inference in the absence of information?
Yeah, in the presence of uncertainty, or in the absence of any kind of inkling to the distributions, to the underlying distributions of how likely something is.
So here's one of the things I do. The most conservative thing that I can say is that I assign a uniform uncertainty. I say anything in this region is equally plausible, and it's fully plausible with a plausibility of 1. I can define that region, I can make it as big or whatever. So it's not frequencies, it's not likelihoods, it's just saying everything in this region is fully plausible. And then I'm going to use evidence to start chipping away at that. Now, in terms of did I exchange probabilities for possibilities? In some sense, it seems that way. But the thing is, in probability, if I say the probability of a collision is 0.7, what's the probability of the not collision?
Simplistically, is 0.3, right?
Right. So the thing is, that's a very hard thing that you're saying. On the possibility side, I can say the possibility of a collision is 1, and the possibility of the not collision could also be 1. I could be fully ignorant of either of those things happening. Those things can exist within possibility theory. It's different. It's more relaxed.
Right.
It doesn't force me to come up with precision artificially.
If I can just add, I was asking you if you interchanged probabilities for plausibilities, not the possibilities. So because you still need to rank.
So plausibilities are possibilities. I use those words interchangeably.
Okay.
I apologize if that confused you.
I'll think about it, but yeah.
That's all right, man. Probably.
Okay, I think we have maybe one more question. Should this be the last one?
Hi there, Dr. Jha. I was wondering if your ideas could be extended to beyond engineering. I was thinking of how you talked about the dangers of binary. I was wondering if you would emphasize ranked choice voting over our current binary system for elections. If you had any thoughts on that, or that's outside your wheelhouse.
So you're asking if I've thought about applying this towards our electoral process?
Yeah, I mean, your whole idea of binary really just in my head it popped up as our electoral system.
Well, I mean, look, let's try it out. Let's model it. Some of this stuff, you need to just try things out just to see kind of what comes out of the whole system. I think it could have merit, but without doing an analysis, I wouldn't know for sure. But on the surface, it seems like it's plausible. All right, I'll stop with the possibility jokes. It's like, here's one of the things, here's one of the places where I've applied this stuff. I'm working with this non-government organization called Global Communities. They got hacked by the whole US aid thing. We got 2 years of data of water, sanitation, and hygiene facilities across Ghana, as well as information about poverty indices and that sort of stuff. And we've been able to successfully use this to help us predict, using the socio-technical configuration analysis, where best to deploy water, sanitation, hygiene facilities to minimize spread of disease, increase quality of life. So this is stuff that I'm using now.